This is a recording for pre-calculus, and this is notes 5.2, verifying trigonometric identities. And there is a handout with problems for students to try for this section after number 5, and I just kind of put what the PDF is called. That's for both you and I to remember what that is. And this is something that definitely 100% you want to be practicing. And there are often many ways to approach these problems, so we don't all have to do this in the very same way. The other just comment I'll make is my expectation is that you are not making too big of a jump from one step to the other. More is usually preferred to less. I will not guess what you are doing, but if you're making a direct change, then usually I can follow that. So verifying trigonometric identities, our entire objective is to be able to verify trigonometric identities. This is definitely something that the more you do it, the more it becomes familiar and easy for you. And so here's our introduction. We will be looking at several techniques for verifying trig identities. And so just a little reminder of kind of past work. So this is a conditional equation that's listed here. So it is, oops. It is sine x equals 0. And we know, if I was going to graph a sine function, that we know, and if I go back that way, we know that it hits sine of x equals 0 at there, and, at an infinite number of places, and that is when x equals nx. And that is when you're doing something like that, you are solving the equation. That is what you are doing. So this is not considered an identity. You are just solving an equation. Likewise, let's just kind of go back in our minds a little bit. If I have 3x plus 4 equals 12, think about how you would do that. You would subtract 4 from both sides. 3x equals 8. Divide by 3. X equals 8/3. And again, you have just solved the equation. You have found the value for x in this situation where the two sides are equal or balanced. And we can't put in any number for x and have that work out. So that is what a conditional equation is, and we're not maybe used to calling it that. An identity is something different. And so what an identity is it's an equation still that looks like this, but it's an equation that is true for all values in the domain of the variable. And then it's an identity. So look at this. If I put a value in for x there and a value in for x there, if that is equal, the right hand and the left hand side are going to be equal, then this is considered an identity. And so an identity is something where it is true for, in this case, all real numbers. And it could be, just for where that is defined. So because of that, there's a few little extra rules that we have to kind of be cognizant of, aware of, excuse me, and as we go through this. So the first thing we're going to do is have a little subpart about, okay, what are our strategies that we want to use as we go through this. And so this is our handout. Oh, and I think I maybe have looked at this. Okay, and I'm just actually truly going to read through this. I apologize if that offends you. But verifying trigonometric equations, that a trigonometric equation is an identity, is different than solving it. And there's no real set of rules to follow that will always work for you. So that's what kind of makes this a little bit hard. But we do have some guidelines. So here are the guidelines, and I have these saved. So, when you're working on a problem, I come back to these guidelines, and I also come back to those basic identity or basic um, identities. And so one method one or guideline one is work with one side of the equation at a time. It is often better to work with the more complicated side. So if we can make the more complicated side look like the simpler looking side, we will have verified the identity. Likewise, think about in the last section when we were simplifying things, if we're working with something more complicated, trying to simplify it, maybe it'll be like that other one. Use algebra, factor an expression, add fractions, get a common denominator, square a binomial, create a monomial denominator. And those are all skills. I'm pretty sure we've done all of those in the last section. And remember, get one term on the denominator, then you can split fractions. You can't do that if there's more than one term without, having kind of a mess sometimes. 3, try to use the fundamental identity. So you want to have those really well figured out in your head. Note which functions are in the final expression. So, if that's what you want to lead yourself to. Also, kind of think about those identities and the Pythagorean identities. Sine and cosine pair up well together. So, if we can get something related to sine and cosine in there, as we look at that, that can help us as well. Secants and tangents pair well together, cosecants and cotangents. When all else fails, or even before all else fails, step or guideline 4 is convert everything to sine and cosine. We tend to be more familiar with or comfortable with sine and cosine. Turn everything into sine and cosine, and then that can make it easier for you as well. And always try something. Always, always, always try something. Even if it leads to a dead end, that can kind of give you some insight into something that maybe doesn't work, and that can be valuable as well. So I just pasted for myself because I have these in my Smart Notebook kind of ready to pull into any problem. And I have these guidelines, and I have the fundamental trigonometric identities. Truly, before you start this section, if you're doing this on your own, maybe pause this, just read through those identities right now, and kind of just make sure that you know what those identities are. So now moving on, verifying trigonometric identities is a useful process when you need to convert a trig expression into a form that is more useful or algebraically. I was going to say geometrically well. When you verify an identity, and so this is also important. When you verify an identity, you cannot assume that the two sides of the equation are equal because you are trying to verify that they are equal. As a result, when you're verifying identities, so listen carefully and make sure you note this, you cannot use the operations such as adding the same quantity to each side of the equation or cross multiplication. So here's a simple equation, 5x equals 15. This is not an identity. What are you going to do on both sides? You're going to divide each side by 5, right? And you're going to get x equals 3. When you are working with identities, you can't do that. The same thing to both sides of the equation. You cannot do that. So you have to work on one side, work on the other side. And there's another method that kind of involves backtracking as we go. If both sides are complicated, we can work both sides and then kind of back copy the other one. So let's move on and do our first problem. Now, I am just going to go through a few problems here and just go through my way of doing them. And I'm going to tell you that for this very first problem, I'm going to do it twice. So I'm going to call it 1A. and it is secant squared theta minus 1 over secant squared theta equals sine squared theta. And you know, in my head, I'm not going to actually keep this here because I'm going to write in yellow. In my head, I think about a line down there, not like when we solved algebra equations way back when, but I cannot cross that line. And so that's one thing that you're going to want to remember. And then I'm actually just gonna, oops, there we go. I'm gonna set up 1b over here because I want to do them both on the same piece of paper or same screen. Secant squared theta minus 1 over secant squared theta equals sine squared theta. And so, you know, if we're just working on the left or the right side, we can just kind of keep putting an equal sign and go straight down as we want to. And that's what I'll be doing. And I'll color code as much as I can. But let me just kind of get everything all situated for myself. And then I'm going to have, you know, this is going to be my little think box over here for this one, and I'll have a think box over here for this one. And really, I just do this very first one twice, not all of them. Don't worry about that. But it's because, you know, sometimes we think, oh, wait, I didn't do it that way. Is mine okay? And often it is. So I am going to use the strategy where I start with the most complicated side first. So that looks more complicated. I'm just going to leave that. And so I want to end up with sine squared. I'm going to do that on both of these situations. And then I'm going to kind of think about, because I have that pretty close by, I'm going to think about my identities. Just kidding. I really meant to pull in that identity page so that I just have it here. And I'll just be moving it out of the way as we go. So for this one, I'm going to notice that I have secant squared minus 1. And when I look at my Pythagorean identities, I have secant squared minus 1 plus tangent squared equals secant squared. And so I can do one of two things here. I can either get secant squared minus 1 equal to something, or I can just say, you know what, I'm just going to put that in for the actual secant squared. And so that's going to actually be my two versions. One, I'm going to just put it in for secant squared. One, I'm going to put it in for secant squared minus 1. And they're not going to be super different, but I think you'll see the difference as we go. So I'm going to remember that 1 plus tangent squared theta equals secant squared theta. And so then, let me kind of size that out a little better. So then I'm just going to take that secant squared, and I'm going to replace it with 1 plus tangent squared. So that's going to give me 1 plus tangent squared theta, oops, minus 1, oops, over secant squared theta. And then I'm just going to put an equal sign because I just know that sine squared over there. Then I've got 1 minus 1, which is 0. So then I'm going to have tangent squared theta over secant squared theta. And I can do a lot of things here with that. Maybe I'm most comfortable with sine and cosine. I want to end up with sine anyway, so I'm going to use these identities. Tangent theta is sine theta over cosine theta. And so if I'm squaring them, it'll be the squared. And I'm also going to use the fact that secant theta is 1 over cosine theta. And so I can square those as well. So on the top here, tangent squared theta, I'm going to turn into sine squared theta over cosine squared theta. And I'll leave my fraction bar in green, and I forgot to put an equal sign there. keep my equal sign there too. And secant squared theta is 1 over cosine squared theta. And then I'm going to invert and multiply is my next thing. I want it to be equal to sine squared. So then I'm going to just write this as sine squared theta over cosine squared theta times invert and multiply cosine squared theta over 1. And these cancel, and I get sine squared theta equals, and just, a little quick check, yes, sine squared theta equals sine squared theta. Please, please, please do not jump too quickly from one to the other, because if I cannot follow it, I will not follow it. And I guarantee that, nobody in the world is going to accept just, oh, there it is, it's verified, because it's not. So the good news is you know exactly where you want to go to get an answer. And then just making sure that you're showing your work as you go. And so now we're going to just change it up a little bit. This time I'm going to say, oh, I would like to change secant squared theta minus 1 into something. And so I'm still going to use that same Pythagorean identity, 1 plus tangent squared theta equals secant squared theta. So if I subtract 1, I'm going to get tangent squared theta equals secant squared theta minus 1. So then I'm going to change that into tangent squared theta. Tangent squared theta. And that will be over secant squared theta. And so that's my kind of, first step there. And then, really I was at this point right there as well. And then I kind of did that same thing. And, truly, I probably would use that exact same process. So tangent squared is sine squared theta over cosine squared theta. And then that is over 1 over, over 1 over cosine squared theta. And maybe in this one, though, I would say to myself, oh, these denominators can cancel out when they have the same denominator. And then I would say that that is sine squared theta equals sine squared theta. So that's my kind of 2 versions of number 1, using those trig identities as I go. So let's look at another one. Here's the verify another identity. If you're in class, I'll ask what side would you start with? We can't cross the equal sign. And so personally, I would say the more complicated looking side is the right side. So I'm going to start with the right side. So I'm just going to leave that 2 secant squared alpha over there. And that's what I want to end up with. Not only that, but I notice that these are conjugates. So when I multiply that, it's going to be super interesting to me because when I multiply those, I think I'm going to get something related to this identity, the trig identity, sine squared theta plus cosine squared theta equals 1, or alpha or u, whatever you want to call it. So let's kind of go through that and see what happens. So maybe I can, yeah, sometimes I've written these kind of a little funny. So there we go. Maybe I can. I obviously had a little trouble writing this the first time through. Okay, so here's my problem. And again, I'm going to have my little think box here. I'm going to tell you that the things in the think box, I don't have to see them. But if they help you to write them on the side of the paper, that's fine. Usually they are things that are okay as direct substitutions. The other thing I'm going to say is, don't start writing all over the page and then like, oh, something's up over here and then it's over there and then it's over here. I have to be able to follow your reasoning, and just trust me, I know that you get involved in these problems, and so that can be hard. But please, please, just show me as much as you can. I'm just going to rewrite this as 1 over 1 minus sine alpha plus 1 over 1 plus sine alpha. And so in my think box, I'm going to get a common denominator. And that is going to be 1 minus sine alpha times 1 plus sine alpha. And to do that, I'm going to multiply, since this one's 1 minus sine alpha, I'm going to multiply by 1 plus sine alpha under 1 plus sine alpha. And we'll put that one in parentheses. Also, this one, I'm going to do 1 minus sine alpha and 1 minus sine alpha. Go ahead and pause this, see what happens. So let's see what we got. I have 1 plus sine alpha plus 1 minus sine alpha all over 1 minus sine alpha times 1 plus sine alpha. And as my common denominator, then 1 plus 1 is 2. And sine alpha minus sine alpha is 0, so that disappears. And on the bottom, I have 1 minus sine squared alpha. And so now, what do I want? I want 2 secant squared alpha. So ordinarily, I might not be super happy with a 2 there, but I have a 2 there, so that actually makes me super happy. And think about 1 plus sine minus sine squared alpha. I can use a trig identity for that. And, is that going to be related to secant squared alpha? And I think it is going to be. So let's kind of see what happens now as we move along. So the trig identity that I'm going to use is sine squared alpha. Oh, I'll use alpha. Sorry, I was going to. Plus cosine squared alpha equals 1. And so if I subtract that, that means cosine squared alpha equals 1 minus sine squared alpha. And that's what I'm going to replace that with, cosine squared. So then this is 2 over cosine squared alpha. And then really just to help myself, I'm going to say, well, that's the same as 2 times 1 over cosine squared alpha. And then I'm going to remind myself that 1 over cosine alpha is equal to secant alpha. And so squaring would be the same thing. And so then I'm going to change that cosine squared alpha or 1 over cosine squared alpha into secant squared alpha. And so that's going to give me 2 secant squared alpha. And I'll just zip way up there, and look, that is 2 secant squared alpha equals 2 secant squared alpha. And so we stayed with the right and just worked on that. Notice I have equal signs there the whole way through, and I can tell step by step I kept going down. Yes, maybe you're using a lot of paper, but just trust me that you want to have things in an organized manner as you go. Let's try this next one. And so this one, let's just kind of look at it a minute and see what we can do here. And maybe we want to end up with tangent squared, or negative tangent squared, it looks like. And these kind of look related to those Pythagorean identities. So let me kind of pull that over. So when I'm kind of making my plan, tangent squared theta plus 1, well, look, I can make that secant squared. I know I want tangent squared in there, but these have things added and ones and everything. Cosine squared x minus 1, I can kind of get a relationship here and substitute that in and see what happens. So go ahead and pause this. That's my hint of the strategy that I would use. Pause this, see what you can get there, and see if you can get it to be negative tangent squared, and then we'll compare. Okay, so let's see how things went there. And so in my parentheses, I'm using this identity, 1 plus tangent squared x equals secant squared x. And sine squared x plus cosine squared x equals 1. So cosine squared x minus 1 equals negative sine squared x. And kind of that's a good thing because I want my answer in the end to be negative. And then when I substitute those two in, then I have secant squared x times negative sine squared x. And so then secant squared, secant is 1 over cosine, secant x is 1 over cosine x. So I can square both sides there, and 1 squared is 1. That's why that all works. So I'll leave my negative sine squared x alone for now. And this is 1 over cosine. I'll think of writing that sine squared x, negative sine squared x over 1. And then that is negative sine squared x over cosine squared x. I know that is tangent squared x, and tangent squared x is equal, negative tangent squared x is equal to negative tangent squared x. And so there we go for that one. Now, moving along, here is our next thing to kind of just write down. Maybe take a minute in your notes and write some versions of those Pythagorean identities. That will be helpful as you go on. So sine squared u plus cosine squared u equals 1. So we want to kind of know sine squared u is 1 minus cosine squared u. Cosine squared u is 1 minus sine squared u. Same thing with 1 plus tangent u squared u is secant squared u. So then tangent squared u we can get alone, and we can get 1 alone as well. You know, kind of that's how the sine and cosine one started. Same thing here. We can get cotangent alone and cotangent squared u alone, and we can get 1 alone. So just, you know, variations of all of those. And to me, you could just substitute one of those in without having to have the other ones as you go there. So here's our problem number 4, and we want to work on this one. The stuff above there is kind of related to that last problem as we look at that. And, you know, maybe we'll find something here. Now, let's look at this one. You know, maybe neither side seems super desirable to you. So we have to kind of pick a side. And this one I'm just going to straight up go through. And what I'm going to pick is I'm going to pick the left side, and I'm going to use sines and cosines. So I'm going to write myself a note of that too. I'm going to use the left side, and I'm going to change to sine x and cosine x. You know, with that hint, maybe I shouldn't have said I'm just going to work right through it. Go ahead and try. Just use the left, change everything to sine and cosine, see what happens. So I've done that. Now I think on that left side, I'm going to get a common denominator. Go ahead and do that. So when I did that, I got sine squared x plus cosine squared x over sine x cosine x. Doesn't matter whether I went sine x cosine x or cosine x sine x. Those are equivalent. Now I'm going to use one of these Pythagorean identities, and I know sine squared x plus cosine squared x equals 1. So that's just going to give me 1 over sine x cosine x, and I did forget my equal signs, so I'll put those in. And now I think I'm going to just separate those, and I think I'll get kind of what I want here. So that's 1 over sine x times 1 over cosine x. and that equals secant x cosecant x. I might just write it here so I can see it. Cosecant x, so that I kind of know as I move down what I want to end up with. So 1 over sine x is cosecant x, and 1 over cosine x is secant x. And then, just because I want to be kind of showing this very clearly, I would use that commutative property and say secant x cosecant x equals secant x cosecant x. I want to get it exactly the same so that there's no question of whether, those are identical or not. So the next one is this number 5. I'm going to let you try that and see what you get, and then we'll go over it together. So this is going to conclude part 1.